Have you ever wondered what's really going on inside your favorite streaming service when it suggests a new film you might love? Or how your email magically filters out all that annoying spam? It might seem like pure digital wizardry, but beneath the surface, there's a secret language at work. This language isn't code, at least not in the way you might think. It's mathematics. In their brilliant book, Mathematics of Machine Learning, Tivadar Danka and Santiago Valdarrama pull back the curtain on this hidden world. They show us that to truly understand and build the intelligent systems shaping our future, we need to get comfortable with a few core mathematical ideas. It's the secret sauce that gives machine learning its power. Many people who are fascinated by artificial intelligence often feel a little intimidated by the maths behind it. Words like calculus and linear algebra can sound quite daunting, bringing back memories of tricky high school exams. But the authors make a compelling case that you don't need to be a mathematical genius to grasp the essentials. Instead, think of it like learning the grammar of a new language. You don't need to be a poet to have a conversation. Similarly, understanding the fundamental principles of these mathematical fields gives you the power to communicate with data, to instruct machines, and to interpret the answers they give you. It's about building intuition, not just memorizing formulas. The journey begins by reframing our relationship with numbers. Instead of seeing them as abstract symbols on a page, we start to see them as the building blocks of information. Every image, every piece of text, every sound clip can be translated into numbers. And once they are in this numerical form, we can use the powerful tools of mathematics to find patterns, make predictions, and create models that learn and adapt. The book serves as a friendly guide, taking us by the hand and walking us through three crucial pillars. Let's dive in and demystify the numbers behind the code. Let's start with linear algebra. If machine learning is a body, then linear algebra is its skeleton. It provides the structure and framework for organizing information. At its heart are two key concepts: vectors, matrices. A vector is simply a list of numbers. Think about a house you might want to buy. Its features, number of bedrooms, square footage, price, can be represented as a vector. For a computer, this list of numbers, like 3, 1500, 500,000, is a neat and tidy way to understand what that house is. It transforms a real-world object into a mathematical one that a machine can process. Suddenly, data isn't just a jumble of facts. It has a shape and a direction. Now, what happens when you have lots of data? Imagine you have information on thousands of houses. You can stack all those individual vectors together to form a matrix, which is just a grid of numbers. A matrix is like a spreadsheet, with each row representing a different house and each column a different feature. This simple act of organization is incredibly powerful. It allows computers to perform massive calculations on all the data at once. Machine learning algorithms can use matrix operations to quickly compare thousands of houses, find the ones most similar to your preferences, which is exactly how recommendation engines work their magic. The book then introduces us to more advanced, yet fascinating ideas like eigenvalues, eigenvectors. These sound complicated, but the core idea is quite intuitive. Imagine you have a dataset that is a big, complex cloud of points. Eigenvectors are special directions within that data cloud where the information is most spread out or most significant. Think of them as the main axes of your data. Principal component analysis, or PCA, uses these concepts to simplify complex data. It helps to reduce the number of features you have to deal with, boiling them down to the most important ones without losing too much information, making the learning process much faster and more efficient. In the world of Python programming, libraries like NumPy are built specifically to handle these mathematical objects. As Danka and Valdarrama explain, creating a vector or a matrix is as simple as writing a single line of code. You can then use NumPy's powerful functions to perform complex operations, like finding the distance between two vectors or calculating the eigenvectors of a matrix. This practical link is crucial. If linear algebra gives data its structure, then calculus provides the engine for learning. Specifically, it's the branch of calculus called differentiation that plays a starring role. You might remember differentiation from school as a way to find the slope of a curve at any given point. In machine learning, this is an incredibly useful trick. Imagine a machine learning model trying to make a prediction. At first, its guesses will be pretty bad. We can measure how bad its predictions are using something called a loss function, which calculates the error. The goal is to make this error as small as possible. The loss function can be visualized as a hilly landscape, where the lowest value represents the smallest error. This is where differentiation comes in. By calculating the derivative, the slope, of the loss function, we can figure out which direction is downhill. If the slope is steep and positive, we know we need to take a step in the opposite direction to go down. If it's negative, we need to move forward. This process is called gradient descent. The gradient is just a multi-dimensional version of the slope. The model takes a small step in the steepest downhill direction, recalculates the gradient, and takes another step. It repeats this process over and over, inching its way down the error landscape until it settles at the bottom of a valley, where the error is at its minimum. This iterative process of improvement is the very essence of learning in machine learning. The model is literally learning from its mistakes. Each step, guided by the calculus of gradient descent, adjusts the model's internal parameters to make its predictions slightly better. Think of it like a blind hiker trying to find the lowest point in a valley. They can't see the whole landscape, but they can feel the slope of the ground beneath their feet and take a step in the downhill direction. This simple yet powerful optimization algorithm is the driving force behind training most machine learning models, from simple linear regression to the most complex deep neural networks. The book beautifully connects this to practice. When you use machine learning libraries in Python like scikit-learn TensorFlow, the final piece of our mathematical puzzle is, well, probability. The world is just full of uncertainty. Machine learning models need a way to deal with it. Probability theory is the language of uncertainty. It gives us a formal framework for reasoning about things that are not guaranteed. It allows a model to say, not just, this is a cat, but I am 95% certain this is a cat. This ability to quantify confidence is critical in real-world applications. Would you trust a medical diagnosis system that was always 100% certain, even when wrong? Or would you prefer one that flagged uncertainty and suggested a human expert take a look? At the core of probability are concepts like random variables, probability distributions. A random variable is a variable whose value is a numerical outcome of a random phenomenon. For example, the outcome of a coin flip is a random variable, heads-tails. A probability distribution tells us the likelihood of each possible outcome. For a fair coin, the distribution is simple. 50% chance of heads, 50% chance of tails. In machine learning, we often use more complex distributions, like the bell-shaped normal, Gaussian distribution. It describes things like human height and measurement errors clustering around an average. Understanding these distributions is key to intelligent guesses. A spam filter doesn't just know for sure whether an email is spam. It calculates the probability an email is spam given the words it contains. So, we've seen how linear algebra provides the structure. Calculus provides the engine for improvement. Probability gives our models the ability to reason about uncertainty. As Tivadar Danka and Santiago Valdarrama's Mathematics of Machine Learning makes clear, these three fields are not separate, isolated subjects. They are deeply interconnected, working together in harmony to make machine learning possible. A neural network represents its data using the vectors and matrices of linear algebra, learns by using the gradient descent optimization from calculus, and often outputs its predictions as probabilities. The three pillars support each other to build one incredible structure. Embracing these mathematical foundations is the difference between being a user of machine learning and becoming a true practitioner. When you simply use a pre-built library without understanding the maths, you are a bit like a driver who doesn't know how their car's engine works. You can get from A to B, but when something goes wrong, you have no idea how to fix it. Understanding the mathematics empowers you. It allows you to design better models, to debug them when they fail, and to confidently explain why your model is making the decisions it is. It transforms a black box into a transparent and understandable system. The journey to mastering these concepts might seem challenging, but the authors encourage us to take it one step at a time. The goal is not to become a pure mathematician overnight. The goal is to build a strong, intuitive understanding of how these tools work and why they are important. Start by playing with vectors in Python. Visualize a gradient descent algorithm on a simple function. Use a library to calculate the probability of an event. By connecting theory with hands-on practice, as the book advocates, abstract concepts quickly become concrete and useful tools in your toolkit. You start to see the maths in action all around you. Ultimately, learning the mathematics of machine learning is an investment in yourself. It gives you the confidence to move beyond simply calling functions from a library and start building, customizing, and innovating. It opens the door to a deeper, more profound understanding of the technology that is reshaping our world. So don't be afraid of the numbers. As this wonderful book shows, they are not a barrier, but a gateway. They are the secret sauce, the hidden language, and the powerful foundation upon which all of machine learning is built. And it's a language that, with a little curiosity and practice, you can definitely learn to speak. Purchase of the print or Kindle book includes a free PDF ebook, Master Linear Algebra, Calculus, and Probability Theory for ML. Bridge the gap between theory and real-world applications. Learn Python implementations of core mathematical concepts. This book is for aspiring machine learning engineers, data scientists, software developers, and researchers who want a deeper understanding of the mathematics that drives machine learning. From vectors and vector spaces to optimization, probability, and complex numbers, the chapters build a rigorous yet accessible path to mastery. Build your foundation, demystify the numbers, and unlock the mathematics of machine learning. Thank you for watching.